Chapter 26 and 27, Density and Contrast. Density. Definition: the degree of blackening on film makes details visible. This is created by the exposed silver halide crystals changing to black metallic silver after processing for film. Two photographic factors allow detail to be seen, both density and contrast. Brightness is density as displayed on soft copy for digital, describing light emission. This is done through window leveling, which produces changes in density, and is done post-processing. Assessing density. Evaluation of the radiograph. Assure the proper densities are present in the ROI, which ROI stands for region of interest. A typical optical density range is from 0.25 to 2.5. When viewing these two images, and this example is in your book on 26-1, the first image that you're looking at to the left of the screen is not good for your clavicle, but it might be really good for your AC joints due to the difference in densities. The image to your right, or the chest x-ray, it may not be good for a T-spine, but again, it might be just fine for visualizing the actual chest. Light versus dark radiographs. Light radiographs lack adequate information, where dark radiographs just have too much information. So which of those do you think would really be better? Obviously, darker images have too much information, and it's better than not having enough. With that being said, again, we still look at Alera, and we still need to make sure that we have our techniques at a adequate level. Lighting techniques. Back in the day of film, we used something that was called hot lights or bright lights, and again, it was just used really with film. With digital optical scanner, again, we can adjust through something like window leveling. And again, with film, we also had something that was called duplication that we could use for copying, and that would allow us to change or lighten our actual films itself. Effects on image appearance. Variables make radiography an art, not an exact science. Factors can affect outcomes. Fortunately, variables usually balance out each other. Rules for changing or changes in technical factors are guidelines. Sometimes they only apply to a range of circumstances. So what do you have to see in a change of density? So remember that we need at least 30% change to actually visually see density. So what should we make changes in? And remember back when we discussed if we actually want to make a change in density, we're going to use it halving or we're going to use doubling. Because again, if it just takes our eye to visualize it at 25 to 30%, then we need to make it big enough so that we can adjust for that. Factors affecting density. They can be either controlling or influencing. So we know that mass is usually our controlling factor, which is the principal method. So what is mass? Mass is the electrons from cathode to anode. And 1 MA at 1 second is this number right here highlighted in red. And this is the electrons that actually are crossing the tube. Again, do you have to remember that for the test? No, but still kind of an interesting fact. There is also another multitude of influencing factors, which we'll discuss as we kind of go through here. Mass reciprocity, it does not apply to digital, and it also fails at extremely long and short exposure times. However, remember the definition is density remains unchanged as long as the intensity and duration are unchanged. There is a figure in your book on 26-2 which will help break down the other factors that affect density. Changes in mass. Minimum of 30% change in visualization of density on radiographic image. Make changes in either double or halves, which we kind of just talked about. Too light or too dark must be a bold action if needing an actual repeat, and then other factors can also contribute. So in this image, and again, this is a figure from your book in 26-3, All of these are at a 60 kVp with no grid. Um, and the first image is going to be at 1 mass, and we're going to double that for the second one at 2. 4 is in the middle, 8 mass, and then the very last image all the way to your right is if we took our second image and only decreased it by 20% from B. And so you'll notice that there's not an extreme difference really in those two images. So again, repeats, you're going to have to actually know when looking at the image the first time how to adjust instead of trying to repeat and repeat and repeat. So if you looked at the first one, you would think, okay, well, let me try this and make it drastic enough to make a true difference. Mass as a controlling factor. The D log E curve represents the exposure and density, which determines the shape and position of the curve. The straight line portion with film density is approximately proportional to the long relative exposure, so it's always a constant ratio. Doubling of mass result in doubling of opacity, so 0.3 reflects the doubling or 1/2 of your opacity. So again, you can kind of remember back to when we did the experiment with our H&D curves or our D log E's that changed the up and down or how long the straight line portion may be. Not always does doubling exposure result in doubling of density. So in digital, remember it's controlled by window leveling, so changes in density or changes in mass do not always control density. Mass is still critical, but brightness again is controlled by the window leveling. It's still your responsibility for an appropriate exposure. Histograms. Representative of the exposure to the image receptor. Manipulation during post-processing can enhance the actual image. Most restrict manipulation in digital systems. But again, it is your responsibility as a technologist to know how to compensate or adjust these. Kilovoltage as an influence on density. Change in kVp results in a change in kinetic energy of electrons in the tube. Therefore, it changes the number and energy of photons in the beam, changes the average energy of the beam. So remember that kVp is that force that drives the electrons across the tube. kVp does affect density, but also contrast and scatter, and will equal to more fog. Small changes can have a profound impact on radiographic density. The 15% rule is just a generalization. Do not use to change density because contrast changes too. Changes in kVp impact contrast. Only change kVp to change density if a change in contrast is also desired. Changes in quantity and quality. Thankfully, too many variables to create a formula. Remember, density is a visual change of 4 to 12% in kVp. No amount of mass can ever compensate for kVp. Generator configuration. Affects the average energy of the beam. The total number of high energy photons in the tube emission is controlled by the amount of ripple in the waveform. It might be more accurate to change kVp to maintain density. So single phase is lower energy than three phase. With three phase, only 10% change is needed, and with single phase, the 15%. So again, you might want to know generator phases and how it controls density. Focal spot size. The larger the focal spot utilizes greater incident electron stream than small. Will not affect density if properly calibrated equipment. If not properly, it should be reported as quality control procedures. If seen, replacement of the tube may be indicated. Blooming. At higher MA, it may alter image receptor exposure. It is not focused on the actual focusing cup. It is rare to actually see with density. Anode hill effect. Alters the intensity of the beam across cathode-anode axis. Density up to 45% greater at the cathode side of the beam, depending on the angled anatomy. So As you can see from the image here, it's just showing you it can be used as an advantage for angled anatomy, more pronounced when collimated, wide open, so we know to always collimate, and then extremely small angles, 12% or less, still have a significant impact. And you do have a table 26-2 that you can look at as well. Distance, SID, alters the intensity of beam reaching the receptor. Inverse square law. So the definition of intensity varies inversely with square of distance. And we remember our formula. You will see the formulas again on this exam. Remember that intensity increases when distance decreases. Intensity will increase if energy increases, and area will decrease. So increase mass when SID also increases, and vice versa. Maintenance exposure. Again, this is used to maintain the image. Again, you're going to need to know the formula for maintenance exposure. Accuracy within moderate acceptance range. Nonlinearity of components makes it impossible to exactly quantify the relationship between radiation beam intensity and film density. Distance. Doubling and halving will bring image receptor exposure within 50% of the original and within acceptance limit. OID, remember, is the object to image distance, and we can use the air gap technique, which increases OID to prevent scatter radiation from reaching the receptor. Filtration. Affects image receptor and density. Types, inherent, added, and total. Inversely related to density. Increased filtration will decrease density. It's rare, but if added filtration is changed, half value layer to permit adjustment of mass. With compensating filters, density is adjusted for filtered and unfiltered regions. Beam restricting. Restricting the beam, collimating, or reducing beam size reduces the total number of photons available. It reduces scatter radiation, overall image receptor, and density. It is inversely related to density, so increased beam restriction, decreased density, because less scatter, less tissue exposed. No adjustments are needed in small changes in collimation. This is showing you an example of the same factors just collimated differently. Beam restriction. Changes in technical factors is required under these circumstances. Large anatomical part, high KVP, low grid efficiency, or non-grid examination. Anatomical part. Patient primary the attenuator of the beam. Size influence exposure and density. It's dependent on tissue thickness and the tissue type. So the average Z number or atomic number, like contrast media. So contrast media is used in X-ray are air, barium, and iodine. Tissue density, or the quantity of matter per unit volume. So it has inverse relationship as tissue type increases, density decreases. Pathology. Remember our chapters on how additive and destructive can change the density of the part. So additive is radiopaic or decreased density, and destructive is radiolucent and increased density. And it just depends on the pathology if it's inverse or a direct relationship. Anatomical part. Part thickness. Variation with large tube angles, and it becomes part of the art. In cast, you should treat as if it's a thicker part. This is just showing you the effect of severe tube angle. Grids. Again, we're going to need to know the grid conversion formula. Kind of remember no 1, 5 to 1 is a 2, 6 to 1 is 3, 8 to 1 is 4, 12 to 1 is 5, and 16 to 1 is 6. They absorb scatter, add exposure to receptor, and density to film. It is inversely related, increased grid ratio, decreased density. The purpose of the grid is to improve contrast. Don't use to compensate density. Film screen combination. Directly related to density. Increase relative speed, increase density. So again, we're going to look at the relative speed conversion formula. With digital images, it can be varied in their sensitivity, and most are calibrated for the images by the manufacturers. Film processing. Time, immersion, direct relationship. Temperature, developer, replenishment rate all have a direct relationship. Chemical activity is directly related. Increase any of the above, you increase density. With that also being said, contamination actually decreases density. So quality assurance of processors can eliminate this as a problem. Table 26-4 shows controlling and influencing factors of density. Assessing contrast. The definition for contrast is the difference between adjacent densities. There are two photographic factors that allow detail to be seen, both density and contrast. Again, this can be seen by the human eye. Contrast is the range from clear white to gray to black. Contrast is needed to make details visible. Dynamic range for monitors or soft copy is window width. Changes density, brightness, and the image contrast. Sufficient difference in exposure to the receptor are necessary for the individual pixels to exhibit different exposure values. It's displayed through bit depth values along the z-axis. Any change in the overall density will affect contrast, most difficult to evaluate and adjust. Describing contrast. The image is considered high contrast when differences between adjacent densities are considered great. High contrast is not always desirable. Low contrast provides actual more information. When differences are minimal, considered low contrast. So fewest shades of gray is high contrast. Increasing the differences in densities increase contrast, produce high contrast. So your table 27-1 is a good reference to describe contrast. This image is just showing you first the one to the left at 80 kVp, the one to your right is at 100 kVp, and demonstrate both high and low contrast. Remember, high contrast is more black and white. Low contrast is lots of different shades in between. The perception problem. Individuals have different visual abilities and backgrounds. It affects their final perception and their contrast sensitivity. Again, already you can probably tell a difference in how you visualize and are able to perceive your images. A lower contrast image often demonstrates more information. More densities are present. Without contrast, no image, all densities would appear identical. Scale of contrast. This is usually a pretty hard concept to kind of grasp. The number of useful visible densities over a shade of gray. So short scale has maximal differences between densities and minimal total number of densities, which is high contrast. High scale, minimal differences between densities and maximum total and number of densities is low contrast. So I think of short scale when I think of, I kind of make the comparison of chest x-rays and ribs. With ribs, we are very black and white, so we have high contrast, but because it's just black and white, it's short scale. And we have a decrease in kVp. With high scale is more like a chest x-ray where we have lots of different shades of gray, so we have minimal differences between. It'll be white, gray, darker gray, black and jet black. And then you will actually have low contrast and high kVp, because remember we do chest x-rays at like 120, and with the rib analogy maybe 70. This is just showing you examples of scale of contrast. Computer digital process. Contrast two classifications, physical or visible. With physical, the total range of density values recorded by the image receptor, max contrast available. Visible, total range of density values that can be perceived by the human eye, compresses information from which diagnosis is made. Manipulating contrast. This is the recorded densities are compression or expansion of the range of visible densities. They can be achieved by a change in the D-log E curve, adjustment to kVp, or adjustment to the window width. Image contrast. There are two types, image receptor contrast and subject contrast. With image receptor contrast, it's the total amount of contrast acquired for both the part and the image receptor. And these can include, like the intensifying screens, film density, D-log E curve, film processing, and digital image receptors. Subject contrast, like kVp, amount of irradiated material, and type of irradiated material. Image receptor contrast, film contrast, range of densities film can record, dependent on these four factors: intensifying screens, film density, slope of the D-log E curve, and processing. Intensifying screens, directly exposed film has lower contrast than screen film. Dramatic change in the D-log E curve when screen film is directly exposed. changing screen speed has a negligible effect on contrast. Film density. This is showing you the effect of film density on contrast. A equals a visible range, B is under, and C is over. The decrease in over and or under exposure occurs because the slope is not steep in the toe or the shoulder decreases contrast. D log E curve, because it's narrow exposure ranges. A is showing you high contrast, which is narrow latitude, and the B is showing you low or wide latitude. It's a major determinant in the physical composition of the film emulsion. As the slope of the curve becomes steeper, contrast increases. Film processing. This is showing you the effect of fog on contrast. A increases for raises toe and decreases slope, which decreases contrast. The developer time, temperature, or replenishment cause an increase in fog, therefore decrease contrast. Developer contamination from fixture causes more fog, which means decreased contrast because of the pH change in the solution. Digital image receptors. Window manipulation is the primary method for adjusting contrast. Most have calibrated sensitivity processing algorithms, which provide linear range of density and brightness. Subject contrast, range of variations in intensity after attenuation of the B. It is dependent on kilovoltage, amount, and type of irradiated material. Kilovoltage and subject contrast. Remember, KVP is a primary controller. It is X-ray energy and penetration. So wider range of photon energy, greater penetrability, greater range of exposures, greater amount of scatter, longer scale of contrast, which is low contrast, and when KVP is low, more is absorbed in the patient, and high subject contrast. So low KVP produces long wavelengths, low energy X-ray. Low KVP equals short scale, which is actually high contrast. This is just showing you the range of transmitted photon intensities and the effect of KVP on subject density. With low KVP causes the lowest and highest photon intensities not to be visible. High KVP, compressed range of relative exposure, reflects within the visible range. Low KVP, expanded range, is unable to reflect within the visible range. This is showing you the effect of scatter on contrast. Scatter produces image density in a region of high subject density. Scatter interacts with image, less contrast, increased fog, decreased contrast. Amount of irradiated material, dependent on thickness of patient or part and field size. Increases in thickness and field size, increased scatter, longer scale of contrast, low contrast. Type of irradiated material, influenced by atomic number and tissue density. High atomic number and tissue density, greater attenuation, larger difference in atomic number and tissue density of adjacent tissues, we end up with high contrast. Evaluating contrast, verify that appropriate range of densities are present. Remember, our optical density range is 0.25 to 2.5. Knowledge of anatomy to determine proper difference in densities is necessary, and then we are about to discuss our contrast mask. This is a contrast mask. It helps focus on contrast in one area. This is showing you an example of a chest x-ray that's too light, making contrast evaluation difficult. The one to your right of the screen, is if it's applied, making it easier. Evaluating contrast. Human eye is limited in ability to discern light and dark. Establishes value for lightest and darkest shades of gray. Each additional shade of gray reduces contrast until not enough difference is to be seen. Selecting the appropriate KVP. Experience and knowledge are key, and already you should be seeing a difference in when you go to do a portable, knowing which technique to use. Low contrast by use of fixed KVP system, high contrast by use of variable KVP system. Must have a 4 to 12% change of contrast to be perceived. 15 to 25% change is necessary to maintain exposure. High contrast is directly related to photoelectric effect. Low contrast is directly related to Compton scatter. KVP controls relation between photoelectric and Compton interactions. Photoelectric effect increases, KVP decreases. Factors controlling contrast. Remember, three things happen with the beam. It's either going to pass through the patient in pure black because it has no atoms. It absorbs in the patient, which is through photoelectric, and becomes white, or it's going to scatter by Compton and cause unwanted densities. So kilovoltage we know as the controller of contrast. So it is inversely related. As kVp increases, contrast decreases. kVp increases, amount of radiation fog increases, and that means contrast actually decreases. These are the influencing factors of kVp. So mass, focal spot size, anode hill effect, distance, image receptor, filtration, beam restriction, anatomical part, and grids. Mass, under and overexposure, moves contrast out of visibility, and we looked at that earlier. Focal spot size does not influence contrast. Anode hill effect alters intensity and affects exposure and film density, affects the contrast, little effect on contrast. Intensity on radiation is greater on the cathode side. Difference only seen in the collimator is left open, and a small anode target angle is used. Distance, source to image receptor distance. SID alters the image receptor exposure and can change the contrast as if there were a change in mass. Object to image receptor, or OID, with the air gap technique, it permits scatter to avoid the receptor, increases contrast. By removing the scatter, you will increase contrast. Filtration, types all, so inherent, added, and total. Inversely related, so increase filtration, increase average beam energy, or Compton, you decrease contrast. Beam restriction, directly related. Increase beam restriction, decrease contrast, increase scatter. Because again, less tissue is being exposed. Anatomical part, dependent on tissue type, thickness, and pathology. As part increases, scatter increases, decrease in contrast. As atomic number increases, or photoelectric, contrast increases. Grids. Function again is to improve contrast, so it is directly related. Increase grid ratio, increase contrast. Our contrast improvement, or K factor, best measure of how a grid accomplishes the removal of scatter, and is measured by our average gradient that we'll discuss in a second. It is controlled by scatter produced and tissue. So this is showing you two examples. The one to your left of your screen is at 80 kVp without a grid at 3.2 mass. The one to your right is 80 kVp with a grid, and we increase to 17 mass. Same AEC and overall density values. Average gradient, or like I said, it's the best way to measure our K factor. So K equals average gradient with a grid and without a grid. The higher the K factor, the greater the contrast improvement, the higher the contrast. Image receptor. So film screen, the D log E curve is the primary determinant of film emulsion, and we looked at that a little earlier. So steeper slope, greater contrast. With digital systems, the difference in exposure are necessary and displayed at various bit depth values. Processing. Increased time, temperature, and replenishment rate will increase chemical fog. Chemical fog decreases slope of the D log E curve, which means we have a decrease in contrast. Helpful hint here, on 27-3 you have a table, and it is a great reference on contrast. For test purposes, you really need to know the differences and what influences both contrast and both density. Thank you. The end.